All right, folks. Let's start with our next iteration of the book club, which is state space models, hidden Markov models. Uh, Today on the technology side, I'm trying a couple of new things. I'm doing some multi-streaming now rather than streaming just to YouTube, which is coming with its own host of, let's say, randomness. The state on each platform we're gonna find out afterwards, but let me know how it is, where you watched from. You can always. It's gonna be interesting because now that we're on different platforms, I guess you can comment on YouTube and on LinkedIn. Probably tweet at me on Twitter. So wherever you're at, let me know. Lars, I thought a couple of the folks here were gonna go to parties and things like that. So I'm excited to see a few of you here. Uh, Glad we have our usual crew. So let's uh, let's jump right into this. I'm gonna preface this one by telling you, I also, similar to Hidden Markov model, went through many different states as to what I should be showing you all. So this is going to be sort of like a philosophical HMM that my brain was in different states, and then I was producing different pieces of content depending on what I was thinking of what we should do for this book club. But I think I've by the end of it I figured out or converged on what I think we're gonna do moving forward. I would love to get your folks' opinions, but for now, you're gonna be in this random walk with me. Ooh, a bit of a lag between the audio and the video. That is something I'm gonna have to fix in future sessions. Let's see if I can do it live, but if not, I will come back and fix that. All right, hoping this is a little better. Thank you, Chad, again. If it's still lagging, let me know, and I'm gonna update the settings again. All right, let's go into what I'm gonna be talking through today. So with our book club, there are a lot of resources. There is there's the book itself. The first one is the table of contents. So there's the book itself. This one. There's Kevin's got so many books. Okay. So there's Kevin's book itself as one resource. We've got the Dynamax docs as the other sort of as the primary resource. Give it a second to load up here. It's always the rule that when you're on live stream, things take twice as long. So we have the Dynamax docs, which are our primary reference. We're going to go through these two notebooks, and then I have my repository. Let me pull that up. So I've been storing the notes in my repository, and I actually have it on an HMM branch. Give it a second again. All right, there we go. So in these notebooks, so everything I'm going to show you is going to be one of at least one of these three, and then there's going to be one more thing as well. All right, Restream is already starting to fail on me, so we'll go back to the chat over here. So I'm going to be referencing this notebook that's right here, discrete HMM. So if you would like to run it, you should go ahead. There's going to be even more nuance on top of that. So let's jump into the notebook and we'll get right onto the Rails. As I mentioned, today is going to be somewhat of a random session, less linear than, especially than the causal inference book sessions that we did earlier this year and last year as well. Doesn't look like I'm going to be running any code today. I don't know. It is taking a while for things to load. Sorry about that, folks. While we're waiting for this to load, I would love to hear from you folks. Any questions in advance or anything that you were looking for in particular out of HMMs? Anything you noticed? Anything that stood out to you? Seems like not much, which is all right. It's all right. That gave me enough time to wait for this. I will figure out why the virtual machine takes so long to run. We'll fix that. But for now, we have our notebook. So maybe as we go through it, something will jog your memory. But for now, let's jump into we got. Theo asks, nothing is Bayesian yet. Actually, okay. Thank you, Theo, for asking. We're gonna. Oh, this is a new thing I'm trying out too. Let's see if I can get it to work. Oh no, I don't have it here. Oh, I do have it here. A chat overlay. So now you folks can see the messages that I'm seeing. All right, that's good. All right. Theo asks, nothing is Bayesian. There is a Bayesian stuff. Actually, I'm going to show you an example of a Bayesian stuff, a Bayesian calculation, just in a moment here. So yes, we do have Bayesian stuff, and I will show you how. I'm going to show you all the details. So thank you for motivating that, Theo. I was a little worried that people wouldn't want to see that, but now I'm excited. All right, so discrete hidden Markov models. Here's our agenda. Key ideas, an overview. I'm definitely going to talk about what confused me. How I'm approaching this is going to be an entire topic on its own. Lars here, I'm going to pull up the chat again. Lars just said the EM algorithm for parameter inference is not super trivial. Yes, I've also noticed it is, before these things click, it is confusing. Not because of the authors. I'm going to say partially because of the code. We'll talk about the code in a little bit. But it takes a while until it clicks. And I have my set of strategies that I've been using that I picked up to get through it. I'm going to show it to you. So we're going to go through those first. And then we're going to go through some examples, a state estimation, parameter estimation. I'll show you the notebook and I'll talk through the example. And then where I would use Dynamax in my past career. I think with Google, my Google examples are less compelling. So I'm going to talk about SpaceX and maybe Sweetgreen. And then an updated focus. So as I was alluding to in the beginning, there's so many elements to this particular iteration that we're doing. It took me a while to figure out what would be most useful for this club in particular. I want to share what I think it is, and I would always love to get your feedback. I'm going to share the summary just right up front because it's going to go so all over the place. I just want you to have the takeaways. So these HMMs can be confusing, and I think actually I definitely know the challenge was between different texts. So ProbML, the website that was referenced in Kevin's book, and then was my primary theoretical resource, and then the code. It was hard to correlate everything initially, especially the first couple of hours. I do like Dynamax's implementation. I've now spent a lot of time with the library just in the HMM module, and there's a number of things I like, which I'll show you, and I'll explain why. There's a couple of implementation patterns that if you're an expert makes sense, but as a beginner it was a little challenging. We can talk through that as well. I do like their docs. So both their the notebook documentation and their API documentation for public facing functions are very good. For internal functions, I wish there was a little bit more, but of course with limited time, that's you prioritize the public ones. Jax is used liberally throughout the library for speedups, like all over the place. I don't say I was worried, but I was curious if Jax was used in one or two spots, but it's used a lot of places, which is really nice because it actually does the speedups internally in the library for where you don't see it, and then the documentation shows you many places that you as a user can use Jax to speed up things even faster. So I'm really, really thrilled with the usage of Jax. And there are many implementations of hidden Markov models. There's actually way more than I expected, so I'll show you those as well. While I move on to the next slides, let me know if you folks have any other topics or things that you wanted to talk about that I haven't mentioned here, so we can cover them as well. In the meanwhile, I'm going to keep moving forward. So here are the references. I've linked all of the ones that I'm largely using here. I'm going to open up this one as well, knowing that, oh, maybe I shouldn't have done that. Oh, I already regret that. All right, folks. This might take a while. For some reason, this virtual machine is really slow. Oh. All right. Full technology day between the different platforms, the VM, and now this. Okay, we still have it. All right, we'll let that load in the background, and then we'll keep going. Yeah, it takes a bunch to get all this whole setup working. So, for the folks who've been here for a while, I think you've seen it getting iteratively, hopefully better and better over time. But let me know, especially Chad and Lars. You folks have been here for a while, so if I'm regressing in quality, I want to hear it. Okay, back to the topic. Key ideas in words. This definitely cut off, so I don't want to exit out. There we go. Okay, so the key idea here, the whole formula that is underlying this all, is this simplified version of the state space model code. So in here, we have our prior for the initial state. This is a categorical. In this particular text, Z is the outcomes, pi is the priors, the prior vector of probabilities. Then you have the observations. So in the dice example that was used, this was the dice rolls. B was the emission probability. And then in the transition model, you have Z, which is the different states. And then A is a transition matrix. And the fact that I can say this all straight, again, took me a while to just get through all of the terms and words and everything like that. It was just... it's smooth once you know it, but definitely it's a lot of terms to start out with. For those unfamiliar, the this big pi here, this is the capital pi, this is lowercase pi, is multiplication. So you're doing, in essence, what is a series of Bayesian updates, a lot of Bayesian updates. So Theo, this is this is a form of Bayes' theorem being used. I'm going to show you an applied example of this in a moment here. There's a lot of terminology, and again, it's duplicated. So we have forward filter, which is estimating the probability using only the scene data. This is implemented. There's a reason I'm calling it out here when we get to the code. Prediction, which is estimating the next time step, what the state will be. Smoothing, which is going the forward-backward pass. This is useful both for state estimation, but then also is necessary for the EM algorithm that Lars had just mentioned. And then there was the Viterbi algorithm, which is the max sequence assignment. So what was instead of just the probability of a state, what was the maximum likelihood sequence of states? I want to open this, but I'm afraid. Let's see. Let me try and open it in a new tab. Maybe this load a little faster. All right, it's loaded a lot quicker. We'll wait for MathJax to catch up. The terminology is I guess I mentioned there's a bunch. There's the stuff that came from, I should label as Dynamax and Kevin's book. Uh, Luckily, those are largely consistent. Uh, they used all of these terms. Now, because it's an HMM, they use different letters than a full state space model, which we're going to get to in future sessions of this book club. But this is what they used, and then the Nippenbutcher article used a whole different set of terminology. So it used X. I think sorry I copied this poorly, but they used X for observations instead of Y, which seems really easy, but it threw me for a loop for a while. They use instead of using yi to t, they use capital X for all of the observations. The transition matrix is phi, I and j are the differing states, and then k was the set of all states. The point being is that it's a fantastic article. Thankfully, they had a lot of examples, but then when I went and to Kevin's book, I would get stuck. So if that's happening to you, it happened to me. It's pretty normal. I would also say that swapping out things like this entire term for alpha also threw me a bit for a loop for a while. So nothing bad, but friction points as I was learning the material. Thankfully, once you understand it and you read a different implementation, it comes faster, but it definitely took a while. So you're going to see me use largely Kevin's symbols. That's our primary text, but I might have mixed in a couple. As I mentioned, the change of symbols within text, the duplication of symbols, then there were the Python variable names, differing usages of words. In the code, there was ambiguous terms. We'll talk about that in a second. When you look at a variable in the code, especially statically, you don't know what it is. And even if you look at the code dynamically, you have to trace back to figure out all the operations that occurred, such as log transformations, transposing, all sorts of stuff. And then abstractions in Dynamax. So Dynamax is well abstracted, which is good for implementing multiple state space models, again, which we'll talk about in a second. But it made it challenging to understand what was going on under the hood. And then there was a whole nother set of things because it's state space models. A lot of time dependencies, partial or not, or time states, and then or things that were completely fixed. So I'm realizing this is going to become a common topic in this particular book club. Let me turn my webcam off for a second. So there are things that, let's go full webcam for this one because this is where I'm most passionate. The things that stay the same the entire time. Like there's one of it and it never changes. So a good example is, let's say, the prior probability. That once you have that, that just stays exactly the same. Another thing is, in this case, was the emission probability matrix. Once you were in a state, the probability of an emission was the same. So in the dice example, it was once you're in the loaded dice state, the probability was, I think, like 1/10, maybe like 1/2 for rolling a 6, and then the remaining split probability for the rest of them. For the fair dice, the probability was 1/6 if you had the fair dice. Those are things that stay the same, independent of time step. Then you had the second thing, which were things that depend on a particular time window, but not the other ones. So an observation is a good one. You see observations, and the observation you get is the one you get, but it doesn't depend on it's now then independent of the other time states. It's just the thing that you saw. That's an obvious one. The one that really threw me was the log likelihood. In Dynamax, there's this array called log likelihood. What it was it's the log likelihood of observing that observation independent of the other observations. Again, confusing. When I say it, I'll show you an example. But it took me a while to realize that in the Dynamax library, the log likelihood didn't mean the log likelihood of reaching that outcome for the sequence of states, but it was just from the emission probability and the observation that you saw at that point. And then, of course, it being a state space model, there were things that just change and are dependent on the entire sequence of stuff. So the state estimation was dependent on the sequence that you saw. Once you were trying to get the probability of being in a certain state, you needed to include the information from every single state prior. And then the emission probability after updating the sequence of state probabilities. Keeping these things straight was challenging because they underlie everything and represented in formulas. You often ended up in formulas. You could see it. Thankfully, you can see the dependencies by looking at the subscript down here. But in the Dynamax library, you actually can't, because a lot of times you just end up with an array and you don't know if that array was conditioned on things or how it was calculated or all of that. So this was particularly challenging when going into the Dynamax library. I'll show you how I eventually unraveled this all. So at this point, I've talked about the first two, how I'm learning, diving into code, and then writing my own mini examples. We're now going to talk about the third and fourth bullet points here. I'm gonna pause here and take questions. Lars asks, "This is only for homogeneous HMM." So Lars, I'm gonna have to ask you to explain to me what a homogeneous HMM is to make sure I understand. When I talk about things that were confusing, some terminology is one of them. So when you mean homogeneous HMMs, could you elaborate just a little bit? Because I want to read your elaboration before I then talk about what am I saying? Things that are relevant only to the examples we read, and then things that are likely going to change in the upcoming examples. A new thing is, because this is going through two pieces of software, it's actually going through Restream and then through YouTube. I don't actually know how long the lag is for questions, so I'm curious to see how far behind this is for you folks. On YouTube, it's about 10 seconds. It's going to be a good experiment to see how far back it is for you folks, whether it's like 20 seconds, 30 seconds, or a minute. While that's happening, I'm gonna set up the code for a second so we can get into that. Okay. I don't know how long it is, and I don't want to wait here for too long, so I'm gonna answer. Okay. So Lars brings up a good point. This is only for hidden Markov models with transitions independent of time. Yes, I noticed something in the Dynamax library that we're going to talk about, that there are HMMs where transitions can change over time, and Dynamax has an API that allows for that. But our current two examples that we're using, the casino models, both the learning and the inference models, they do not have time varying transitions. That meant that once you had the loaded die, it would give you the same answer regardless of when you got it. Theo says it's about 20 seconds delay. Okay, good to know, Theo. There's going to be a little downside of streaming not straight to YouTube, but through Restream. Okay. Lars says this assumption is often made. Yeah, let's talk about that later as well. So, in our two examples that we're covering just for this session is the transitions are not time varying. They stay exactly the same. You can see that in the code. Well, in this diagram right here, and then in the code right here. But let's talk about the time varying transitions in a moment. All right, what I'm going to jump into now is going to be about a 2 to 3 minute monologue of how my thought process of how I went through this, how I unraveled it for myself, and now how I feel like I have a confident understanding of the theory and the code put together, not just one and other independently. So we're going to go through a notebook. Let me turn off the chat overlay and my window. We're going to go through a notebook, and then we're going to go through PyCharm and some modified code. So here's the code. The top part is going to look very familiar. Now I'm going to point out this is running off of a modified version of the Dynamax code base. There's some changes I made. We'll talk about those changes. I feel like they'll be useful for you folks as well, just as techniques. So I'll highlight that in a second. But let's start with the easy part. The example was a biased coin flip example. Sorry, the example was a biased dice roll example. So this was nice because Kevin and Atal showed you that the transition matrix could be that the emission probs could be a different size than the transition matrix than the initial prob. So it was nice as an example for them to show that things could be different sized arrays. Sometimes it feels like when people use 2x2 and then 2x2 arrays, or 1x2 and 1x2 arrays, you implicitly think those have to be the same, but they showed that it didn't. However, for the purposes of learning, it's a lot easier to simplify things. So instead of a biased dice, I just changed this to be a biased coin flip. So now we're not having 6 possible state emissions, 1 through 6 on a dice. We're just having 2 possible state emissions, which is 0 or 1, or heads or tails on a coin. And we have that here. So we have the number of classes being 2. Copied this twice by accident, so just ignore one of them. The other simplification I made is for the transition matrix. I'm just assuming there is no transitions. So this eliminates the chance that you can go from a biased coin to a fair coin. Once you're in one, you stay stuck. This will simplify some of the calculations I'm going to show you later on. Put in some emission probs for the fair coin and for the loaded coin, and then we initialize the state space model. So in this case, this is actually something I really like about the Dynamax library. Let's switch off of the theory and let's talk about the library itself. The pattern they use is this stateful object-oriented pattern where you instantiate a model. You instantiate a model here, the categorical hidden Markov model. I could have used the Bernoulli hidden Markov model API, but I stuck with categorical for this one. You then call initialize. A bunch of stuff happens under the hood. I didn't look at this initially, but when I looked at it later, realized a lot of things are happening here. So you call initialize. And then the nice thing is once you've done that, you can do things like sample. So just as they did in their notebook, you can sample it, and now you can get some data out. You get back the true states. So in this case, we were with the bias coin the whole time through, and then we'll always get a sequence of ones. So we're always getting heads with our bias coin. And now that we have some data, we can actually call filter and again, when you call filter, a bunch of stuff happens. And when you run filter on your code base, you're not going to see any of this. When Dynamax just does it implicitly, not implicitly, but like Dynamax doesn't print the calculations to console. It just does them. But I have modified Dynamax to start showing all this stuff because, as Lars had earlier pointed out, when you call some of these things like filter or smoothing or SGD, there is so much happening under the hood. And you just sort of get the result, which is nice. But when you're trying to learn it, you're wondering what the hell is going on. So let me talk through what I've added, and then we'll go to the code base, and then we'll come back and talk about these numbers. So what I have is I have it print out the initial state probabilities, the log probabilities, the predicted probabilities, the log likelihood of emission given a state, the filtered probs, and then the predicted probs. So it's just off the bat, because it's computation. For the folks who don't know, often when you do probability calculations in your computer, you often want to do them in log space. This is due to numerical stability. I'm happy to show you an example if anybody wants to see me talk about the details of numeric stability, but let me know in the chat. I don't want to belabor you with a boring math explanation of log transformations if nobody wants to see that. But since we're here, just know that a lot of things get log transformed almost immediately, but some things don't get log transformed immediately. So as users, we specify things in non-log space, in just regular probability space, but under the hood, things get transformed into log probability all over the place in Dynamax. And when you're debugging it, you just have to know whether you're working with log probabilities or whether you're working with normal space probabilities to understand what's happening in the calculations. So log probabilities aside, we see that the log likelihood of emission state does not change between the three. This was the first thing that threw me for a loop. I was like, what? Why is this not changing? Like, I do not understand how the log likelihood of emission is not changing. And then it finally clicked that it's just in the code, it's given the state. So the way Dynamax works is that it just takes this the likelihood of emission given, assuming for both states, then it prints them. So this is 0.5 and this is 9/10. I'll show you the calculation again in a second. What it is doing though is it's updating the filtered probs and the predicted probs. So in this case, you can see that you get a filtered prob, and we're I think I did the transformation. I have to double check. Actually, I did, because it adds up to 1. That in the first case, you're like, okay, I got 1 heads. It's 64% chance that I have the bias coin, and then I get a second heads, and then it's a 76% chance that I have the bias coin, and then I get another heads, and then it's an 85% chance of getting the bias coin. And so you're like, this is the state probability updating in the code, and then we get a predicted probability, and these right now are exactly the same. They're not going to be in a second, but for now, what's happening is it's then predicting what the next probability of state is going to be. So in the Dynamax code, it's doing these two steps in conjunction. Again, this took me a while to wrap my head around. I was like, why the hell am I getting 2 different probabilities for state from Dynamax? It's because you're getting the one that's a t, and then you're getting the one that's a t plus 1. In this case, because the transition probability is exactly the same, the transition matrix means that once you're in a state, you're just stuck in that state. They stay exactly the same. So once you have a bias coin, that you're guaranteed to have the bias coin the next time, which is why this is staying exactly the same. But again, I'm going to show you a permutation of that. All right. So now we're going to take another tangent. I'm going to jump to the code, and I want to show you what's I did and what's different about it. So what I'm doing is I'm running this notebook on a version of Dynamax that I have modified. I'm going to hope this loads fast. Let's see. Okay. So I have collapsed this to 1 commit, but essentially what I did is I went into Dynamax, and I found out where all this all this stuff is happening, and put in Jax debug print. So for you folks learning, this function Jax debug print is really, really, really good. I won't do a Jax tutorial here, and I'm hesitant to do it live. Maybe I'll try doing it live, showing you the debugging. But now we're gonna switch to a whole topic about Jax. In the chat, please let me know if you folks are familiar with Jax, if you've ever used Jax. I'm gonna do a quick overview now while I wait for that 20-second lag, and then I'm curious what you folks say. In short, though, just real quick. Oh, this is a total aside, but I just want to self-promote. I designed this entire homepage for Jax. I had some help from Jake Vanderplas and this really nice game named Ozhaas as well, who's a huge contributor in open source. But I'm like so proud of how this documentation page looks, because if you saw the earlier Jax documentation page, it was just a whole ton of links, really hard to read. Just really happy about this. Anyhow, self-promotion aside and self-aggrandizing, Jax is a library that provides numerical speedups to NumPy. Sorry, provides numerical speedups for computational code. And when you use it, it's a great library, but it does all this magical stuff under under the hood. And so when you try and debug, you can't actually see the values. There's sort of these just-in-time compiled things, and when you look at the arrays, you just get this thing called Jax array. So what you need to do, or a functionality that Jax provides, is to print the values. You have to call Jax debug.print, and then it'll print out what's going on. What I did is I eventually we'll talk about this. I want to pull up the whole file. Let's pull up the whole file. It took me a while to figure out where stuff was going on, because it's not happening in the categorical HMM module. So it's not happening. The stuff isn't happening here. I know the font is a bit tiny, so I think in the future I'll figure out how to make it bigger. But it's not happening in models. There's very little happening in this categorical HMM module. Let's see if I can do this. Make this bigger for you. All right, next session I'll make this code larger. Sorry for the tininess. Very little is happening in here. This is doing an initialization and stuff like that, but the calculations don't happen here. The calculations happen actually in abstractions and in other places throughout the library. So it took me a while to find that, to get to the abstractions and then actually get to the part that we probably care about the most, which is inference. But once you're there, you can just see everything that's going on. So I can make this one bigger for sure. Okay, here we go. So this is where all the magic is happening. Lars had mentioned earlier that the EM algorithm and stuff like that is non-trivial. He's right, and you're seeing a lot of the code that runs the backwards pass and the forwards pass all in here. And so if you're a person that's trying to learn the computation, this is the place you're going to be for HMMs. You're going to be here, and you're going to be looking at all of the mathematics that are happening, largely in this module. This is really the meat of it. And it's not unfortunate, but another thing you're just going to have to get used to, which is another hurdle for me, was the code does a lot of I want to show you. It's what's a one-liner in any of the other articles, like in here, like this. Okay, this is the same thing actually, right here, the forward algorithm. So here's the forward algorithm here, and here's at least part of the forward algorithm here. What is a one line in either the book or the explanatory web articles is 4 lines here. So what's happening is this is actually doing the Bayesian update, the conditioning, but it's doing it in 4 lines of code because it translates it into well, it's sort of already in log space, but it's doing the log space calculations rather than the straightforward like regular space calculations, and you just also have to get a sense of what's going on here. If anybody wants me to do a video on how this is working, let me know. I'm just happy to, but as you can see, there's already so many topics happening in this book, in this particular session, that I always got stuck. Like, do folks want to see this? Do folks want to see this? Do folks want to see that? So, all right. That aside, once you do all that, once you add all those array stuff in, you get this output. So, if you folks want to run it yourself, you can certainly modify your own code base. I can also show you how I'm running a version of Jax that's modified in my state space model notebook. But highly, 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 highly recommend whatever thing you're trying to learn, whether it's EM, conditioning, or filtering, come in, add some print statements. That helps a lot. The other thing that I did, I'm going to see if I can do it live, is just run the PyCharm debugger. So as a person that also tends to program a lot and I program for work, is when I'm developing libraries, I tend to use PyCharm more. So, to answer a question that came up in the last live stream, which was, do I use PyCharm or notebooks? The fact of the matter is I use both quite heavily. I go in here and I put a lot of debugging breakpoints in. This virtual machine is running particularly slowly today, so I don't know how long this is going to take for it to do all of the steps. So we may not wait for this, but using either the debugger in Visual Studio Code or the debugger in PyCharm or any other like full-featured IDE was absolutely key for me to figure out what was getting called where, because it's not, again, in the Dynamax code base, which I'll flip through. It goes. There's a lot of while this runs, I'll show it. Maybe I'll show it here. There's a lot of abstractions. I mean, there's a whole module called abstractions. So you get a call to categorical HMM that imports from the state space model initial thing. So this particular class gets instantiated from another thing that's called emissions. There's this entire thing called initial, which has some imports in. So code is going all over the place, and using a debugger was absolutely key for me to figure out what was going on. It doesn't look like, well, maybe it'll actually work. We'll give it a second. I'll show you the debugging in a second. It's taking a little bit longer. So let's jump back to the notebook. All right. So that all aside, the reason, it finally came up. So, okay. In my debugger, step into it. I get to this. I had to modify the codes a little bit more because there's this pattern that they like using a lot. I wish I could make this bigger for you guys. All right. I'm not going to be able to make it bigger today. I just broke the code. In the code, there's these patterns where you have a function and it immediately is giving you the output of another function and just splatting the operator so you don't even know what the outputs of this function are. So I had to go in and modify a lot of it to make the arguments their own, assign them to their own variables so I could see what they are. So then as we step over the code and go through things, I can actually tell what is getting fed to what function. So now we're at the filter function. This is doing some jack stuff, so we don't do that. So then go to filter, blah, blah, go in here. There's even more happening here. That's the way it took me to learn this. All that craziness aside, let's talk through what's happening finally in the computation. So now we're in the state of the book club where I was like, okay, let me explain the computation. We just exited the state where it's like, let me figure out how the computation even works. To the folks that are talking about JAX conceptually, I might do a live stream where, let me know if you would like me to do dedicate a portion of the next live stream to talk about JAX. The reason I mention that is, besides it being used very liberally throughout this library, it is a very useful tool that's used all over data science these days, from neural nets to HMMs to Bayesian inference to oceanography and all sorts of stuff. So it's really, really interesting. I think a quick 20-minute tutorial may help you folks, but let me know. As you can tell, a lot of things going on. Okay. What I want you folks to remember is three numbers. I'm going to post them in the chat so you have reference to them. I'm going to post them only in the YouTube chat because Restream is messing up on me. So there's that one. I want you to pay attention to this one, and I want you to pay attention to this one. All right. So how are we getting that numbers? The first one is really straightforward and easy. What we want to get is the log likelihood verification first. So where are we getting those initial log likelihoods? 0.69, 0.105. Where are they coming from? We can replicate this with SciPy stats. We have our probability of heads from our biased and our unbiased coin. That's 1/2, and that's 9/10. 1 represents a head. You call log a probability mass function because this is discrete, not PDF. If it was continuous, and you get these two numbers. They look exactly like the numbers that we got here. So, perfect. That one is straightforward. In Dynamax, these stay the same no matter what the time step we're on is. Now, the next question is something has to change with time step. All right, there we go. Something has to change with time step, and that is the Bayesian update for filtering. So I think Theo had asked, are we doing Bayes theorem here? And the answer is yes, quite frankly. So here's a lot going on in this virtual machine. Here is the Bayesian update. I haven't, you got the likelihood, you have the prior, and you have the total probability. And if you do all the calculations, you get 0.64. If anybody wants me to talk about the Bayesian update in more detail, let me know. I'm always happy to do so. I love Bayes theorem. But here's the Bayesian update happening, and you'll notice that this number is, exactly the same. Oh, no. My computer froze. It's exactly the same as this number right here. Of course, the converse, because it's a two-state probability. If we do the opposite calculation, you would end up with 0.35. But here is how you get 0.64, and then let's get 0.76. You're getting 0.6741. So Theo asks, we are getting the map rather than the full posterior. All right, Theo. Let's pull up the chat window. So maximum A posterior. He asks, we are getting the map estimates. Is the posterior coming later? So the first answer is, in this particular example, this is the full posterior because this is a Bernoulli case. There is nothing, there's no other, there's no beta prior that's continuous or anything like that. Like if in this formulation of Bayes, this is the map and the posterior are exactly the same, which is the beta distribution. So that's the first answer for full posterior. There is a more nuanced answer. We're gonna take another side tangent here, which is in Dynamax the priors are actually not the Bernoulli priors that you put in. So at the user level, we're putting in what do I want to show this to you? At the user level, we're putting in these point probabilities, 0.5 and 0.5, right? So these are just singular points. But then internal to Dynamax, and let's see if I can find it for you folks. Dynamax is actually turning these into Dirichlet priors under the hood. That is a really big thing to just say in one line. Text slowing me down. It's turning them into Dirichlet priors right here using TensorFlow distribution. So a whole nother side, the TensorFlow is used throughout this library in various spots as well. That's a whole nother topic that we won't talk about today, but it is turning those point probabilities into Dirichlet priors, which are then distributions. I'm going to pause on that thread here. Otherwise, it's a whole nother thing. If anybody wants me to talk about Dirichlet priors or distributions, also let me know in the chat. All right. So for now, though, we have verified the at least forward filtering calculation that Dynamax is doing. So this is what's happening. The key point I want to make here is this is everything it took for me to understand what was happening in both the hidden Markov model, theoretical documentation, what's happening in Dynamax, and then tying it to all my other Bayesian knowledge. It was sort of like a big process to go through a bunch of different threads and then have them consolidate into one. So summarized, for folks that are trying to learn and folks that were curious about my thought process, it was a lot of reading these things and getting used to correlating between these two first. Like, am I getting the understanding between these two things? Because they're both explaining it, of course, in different styles, but can I get the symbols and everything right between these two things? Then it was, can I verify my intuition in Dynamax? So can I make a really simple HMM Python script, largely copied from the docs, and do I just understand what's happening? So at the user level. And then it was a whole process of, can I then dive into JAX and Dynamax and understand what was happening there, which finally led me to this point that you see here. So that's what it took to get here. You don't have to necessarily follow my craziness, but between all of that, I hope you've seen a couple of different strategies that help you learn the area that you were looking to learn. With that revelation, then it was just a matter of making small mutations on things and then seeing what happened. So now the small mutation I'm making is I've changed the transition matrix. Now instead of being stuck in the probability that in the state that you're in from the beginning, there is a chance that you can start in either state. So there's you could be here, or you could be here, and there's a chance that once you get from you could start with the fair coin, but once you get into the bias coin, you're just stuck at the bias coin. Subtle perturbation that makes things a little bit different. And now here's where you start seeing that the filter probability, which is the probability of state at the time that we're at, and then the predicted probability for the next time step are different. So the filter probability stays the same for the first step because the initial starting state is exactly the same. It's 50-50. But then once the predicted probability is different because there's a chance we could end up in the bias coin state and switch. And then once we're there, it becomes like pretty certain that we're more and more likely to get stuck there. So once the probability of being in the bias coin state goes up and up and up, because it's more chances that we get stuck at the bias coin. So there you have it. That's how I learned at least that portion of the stuff. Now we're gonna flip into another mindset of the book club, in that I realized I don't want to do that over and over again and explain that entire thing to you. So now we're gonna flip to the second state that I ended up in. So that was my let me figure out everything that's going on state. Then I ended up in the state that well, now I need to flip back to real world examples. So we're making a transition here, and then I will explain the overview at the end. Thank you, folks, for sticking with me. So certain things that are important now that we're back here, it's as a practitioner, what's the computational complexity? The forward algorithm, the computational complexity was fixed, and you know it, and it was so not the same, but there was also one for the backwards. It's what's O to the TK, which means the number of states. It's linear with the amount of time steps you have, and it's quadratic with the number of states. So 4 states is, I shouldn't use 4. 8 states has much higher computational complexity than 4 states. But you can just make these things really long, and it won't take too much longer. JAX helps a lot with parallelization, which is another topic that we'll cover in a second. Right here. So JAX provides a number of speedups, which will make these things a lot easier to use, or a lot faster to use. So if you have a bunch of different dice situations, so not just dice rolls, but different in a casino, let's say you have a number of different dice tables. Using JAX, if we want to make I'll close this out now so we stop getting that error. Exit. Ooh, okay. So JAX practically will give us speed ups in parallelization and in computing the gradient, which again I'll come back and talk about in a second. So, all right. So I'm gonna frame my real world example, and then I'm gonna talk about the previous 2 points. Let me just actually look at what my next slide is, super quick. I'm actually worried this is gonna take a while to load, so Let's see if we can get it. Otherwise, I'll just post the link. Let me actually just post this in YouTube for you folks. So you can probably see it on your end because it might take a while on my end. Of course, we're going to get a bunch of ads. So what I'm going to talk about is SpaceX. So for those who don't know, I worked at SpaceX. It's actually where I got interested in all this stuff, was at SpaceX. So this is actually the factory that I had worked in. This is in Hawthorne, California. That's where it was for a number of years. Of course, there's Elon Musk, who's everybody's most famous CEO celebrity, giving a tour. But here's the important part. Okay, here. Oh no, I hit the wrong button. It was here. Okay. Here's what's important. In this video, we have a bunch of Haas machines. These are Haas CNC machines, and there's 3 of them here. There's actually many more at SpaceX. At SpaceX, these machines are producing parts, and all these rocket parts are going to go onto a rocket. So here's the questions: are the parts good? So, which is one question. Like, is the part that we're producing a good part or a bad part? And machines can produce good parts or bad parts in any state, but in certain states, they tend to produce more bad parts or entirely bad parts, always bad parts, than sometimes good parts. So these were, in my situation, the casino dice rolls. It was every single time we end up with a part from this machine, is it good or is it bad? That's the emission. And then I also wanted to know what state the machines were. Were the machines in a good state or were they in a bad state? And then it actually was also interesting whether the machines would transition from a good state to a bad state, either just once or whether they would go back and forth. So these were the hidden Markov models that I had, or this was the data generating process that I had at SpaceX. And this is where hidden Markov models would have been so useful, had I been better at, and had I had Dynamax at the time. In terms of computational speed up, the question becomes, because I'm at a job, I need my models to run quickly. In this case, because it was just a state of bad or not, they would have run pretty quickly. There's only 2 states. And because there's 3 machines producing 3 independent time series, JAX would have provided awesome numerical speed up because it would have been running the filtering and smoothing algorithms on different threads that are like non-blocking each other. That's how the real world gets into my computational space. So I've got a bunch more to say there, but a ton of things have happened in the chat. So I'm going to stop for just a moment. We're going to go through the chat, and then we're going to come back to this real world example. Of course, feel free to keep loading up the chat with examples, with questions. So the questions I got are, James says, thanks for the stream. I appreciate that. Theo says, full posterior coming later. Yeah, Theo, I'm going to talk to you about the full posterior because we're going to talk about OptAx, expectation maximization, and stochastic gradient descent. It's a really important topic about the full posterior for a number of reasons. So we're going to take your question a little bit later in this live stream. Yuri says, states, was that HMM states? Can you actually do HMM with 6 states? I have limited experience. I always saw 3 to 4 states. So Yuri, the good news, as we've been covering in this book club, is yes, you can do HMMs with 6 states, 6 emission states. I'm sorry. Can you do an HMM with 6 states that are latent? Yes, you can. You just have a bigger transition matrix. This is a 2x2. I can't. This is another challenge with this book club, and we're gonna talk about this again at the end. There was an HMM that I ran, not in Dynamax, but actually in PyMC. That was an HMM that was at 60 by 60 states. This was a particular client that we had at a company I had worked at, where the state machine was, the process was, a house is in foreclosure. How long does it take for the house to finally end up going back onto sale? And the reason it was an HMM, for folks who don't know, is in the U.S. In different counties, which we'll also talk about in a second, or different geographical states like California, Arizona, Florida, New Mexico, New York. When a house is in foreclosure, it takes a series of steps for it to finally end up going back to being on sale. So it's got to foreclose. A lawyer's got to do some paperwork. It then goes to a court. The court does some paperwork. In some states, the lawyer then has to do more paperwork, and then it goes to a county assessor, and then it goes to this thing, and then it goes to that, and then it can finally end up going to sale. The kind of annoying part is that it's not always guaranteed the process moves forward. Sometimes the judge can send stuff back to the lawyer to redo the paperwork, to send it back to a judge who sends it back to the lawyer before it goes to the judge, before it goes to the next step. And then sometimes if the judge has sent it back, the lawyer can skip the judge the second time, right? So now you've ended up with this insane transition probability matrix where on the first transition, it's probable, but then on the second transition, it's not allowed. And then also this particular client, the emissions weren't the emissions were time. So the emissions were posteriors that it's going to take between 2 to 10 days, or that it's going to take between 2 to 8 days, or it's going to take 8 days always, or it's going to take a month. So this is the HMM I was working with. It was like, I think it was like, well, first off, it differed by different geographical states, because California would have a different process than New York, but it was like a 45 by 45 transition probability matrix. Portions of it were hard coded. So you knew that you couldn't go from foreclosure straight to sale. Like, that was impossible. So we eliminated those. And then we had to then estimate both the state transition probabilities and the emission duration probabilities on a continuous scale from observed data. So we had a bunch of observed data of all these things happening, and had to do that. That was my very long answer of telling you that there can be HMMs within a lot of states, like 60, 70 states. And this is an example of HMMs being used in practice, of this particular person trying to essentially do real estate flipping by understanding the duration of timing. And if he had a house that was in foreclosure, how long would it take before it could go back on a sale? Would it be 2 months? Would it be 6 months? Would it be 8 months? Given the data for New York, if it was in the lawyer's hands, how long would it take? What's the probability it was going to go back to the lawyer? And they were building this tool to help realtors understand their portfolio of houses and which ones they should pay attention to and which ones didn't. So realtors are dealing with 60, 70, 80, 90 houses, right? And they're all in different states, but then it becomes a question of where are they going to go in the legal process and the sale process. And he was building this tool to help him do that. So I wish I could show you that. I am not allowed to show you that, but that was an example of a discrete case hidden Markov model, the biggest one that I personally have worked with. And coming back to our good friend Elon Musk, or at least my old boss Elon Musk, this was an example of state-based models that I would have used. That I would have used at SpaceX at the time, had I had the skills that I had now. Now, it was really important to know which parts were coming off and which machines we needed to fix. And we were doing that sort of, let's say, intuitively, using intuitive Bayesian methods to try and do that. But state-based models would have been awesome at the time. All right. Tying that back to the terms. I don't know why this notebook keeps changing. Sorry, folks, that we keep getting this pop up. Questions that were asked to me when I was at SpaceX. What state is the machine in? Are we going to get good or bad parts? How often does the machine tend to switch states? Like, once we've calibrated a machine and we paid for the people to come in and inspect it and like laser guide it and do everything, it's a whole process to get these machines calibrated. Just so you know, there's sometimes you have to do it in house. Sometimes you have to call in these folks that have these like lasers that line them up. It's like a lot. does it tend to switch back and forth? Like, does it stay bad, or does it switch back and forth? Because if it stays bad, that's one problem. If it's switching back and forth, that's another problem. So is the machine state switching? And then what's the probability that bad parts are coming off of this line, or in this case, this machine? So what's the probability that this machine was giving us bad parts, but this machine is giving us good parts? All super critical questions when you're launching rockets under Mr. Musk here, who, as you know, really wants you to build things fast. So my data in this case was parts that were produced from the machine. I had a table where I could query and see every part that was produced from that machines. I could also see which parts were good and which ones weren't. This was in a quality database. And then I had the parts from many machines. So it wasn't just one machine, but a whole bunch of independent time series. And now the words I would have used is smoothing. So in my case, it being like a week later, I could smooth to see the probability of the machine being in a bad state, given all the data. I certainly would look for correlations. We have not covered covariates in this book club yet because our current notebooks are not using covariates, but they're fully supported by Dynamax. Then there was parameter estimation, which that's a topic I haven't touched on in a second. We'll get to that for some of the questions in the chat. But how faulty was the machine? So not just when was the machine faulty, but was the machine breaking a lot or not? And then filtering is what state is the machine in now. This would have been a little bit tougher, much tougher in my situation because I didn't get the observations of the final emission until a day or two later. You have to produce the part, and then a day or two later you get the inspection report of whether it was good or not. So filtering would have been more challenging. Probably wouldn't have been able to use filtering, but definitely would have been able to use smoothing. Useful extensions. These are supported by Dynamax, and we're going to talk about these in future book clubs, but it's the covariate hidden Markov model. So hidden HMMs that can take in observables such as machine temperature, time, part setting produced, the operator. These are all things that affect the quality of the part. And then autoregressive HMM. So it's in the physical case with machines, it's not totally random. Like as the machine tends to become more and more faulty, it tends to become more and more faulty over time in like a way that it can be modeled either with covariates of time or autoregressive that you look at the previous states and then start understanding that it probably is going to become faulty in the future as well. That's my real example. Let me go to the chat, and then we're gonna then jump to another state in our book club, which is me talking about what we're gonna cover next. So another state transition in this lecture. All right. Yuri says states was that HMM states. Can you actually do HMM with 6 states? I think okay. I answered that question already. Tyler says bouncing off that, is there a maximum number of states? Is there some generalized form of infinite states? So this being a practical book club, Tyler, it seems like there's going to be a maximum number of states that's computationally practical because using these forward filtering and backward filtering algorithms, the computational complexity is t to the k squared, where k is the number of states. So at some point, I think if I had 100 states, that I haven't actually tried it. This will actually be something that maybe you folks can try. Create a couple of these models. Maybe this is a good homework assignment. Create a couple of these models and then start making the states larger and larger and larger, and then just see the number of states larger and larger, and then see at what point it just takes too long for it to be useful. So theoretically, there's no practical number of states, but practically, it looks like there is definitely a practical number of states. But then there's a more implicit question here: is there some generalized form for an infinite number of states? And the answer also is yes. We haven't gotten to that yet in this particular book club, but the generalized form is right here. These probability distributions could be anything, and this particular common filter shows you an example where there is an infinite amount of places you could be in this case 2D space, but in the real world 3D space, and yeah, every individual point in the world is a different point. So yeah, also yes, that there could be an infinite amount of continuous an infinite amount of spaces if we use a continuous space model. Charles writes, I suppose you could write down a sequence of HMMs that converge to a common filter. So Charles brings up another whole thing about this book club that we're running right now. Is I'm realizing that there is a lot of theory that you can use in this book club. Like it's actually even written in the notebooks themselves. So Charles, there are so many angles to like if you do this, if you do that, if you change to this or change to that, like something is theoretically possible. It is like absolutely fascinating to me. And so all these little perturbations that like you make this one assumption and then like this whole other class of algorithms and things opens up. So Charles, I'm going to come back, or Charlie, I'm going to come back to your question as well. Coming back to the concrete world before we jump into Ravine just starts talking about random stuff again at the end. There are a ton of state space model APIs in Dynamax. I actually had not looked at this before very closely. I just looked at the notebooks and I'm just like flabbergasted by the number of implementations there are. So there's Bernoulli HMMs, which is the simplification I could have used, but then there is so many HMMs: diagonal, shared covariance, Poisson, more diagonal Gaussian mixtures, linear autoregressive, logistic, so on and so forth. So there are the number of docs here. If you just look at these, you'll be severely underestimating the amount of permutations and combinations of different distributions and things we can do with Dynamax. So I'm particularly pleased, I have to say, as a practitioner, that this toolbox has so many different tools to just pull out, and they all work. And then the cool thing is, if you look at the code, I won't pull it up right now, but there are even more things that they are planning to build into here. So different initialization algorithms like k-means, which would be really nice because then you don't even need to specify the prior probability. You can just give it a sequence of data and it'll just like figure it out for you, which is so nice as a practitioner. There are other implementations that are in there but have been commented out. So it looks like even more to come from Dynamax. Really, actually, as you can tell, I'm pretty excited. It's really, really nice to have this toolbox. So let me flip to the other notebook. I'm only going to go through it super quickly because I realized even when I was writing this that this book club was going to take forever if I went through everything. So let me go through parameter estimation at a high level. I'm going to answer 3 questions that have been posed here. One question is the full posterior available? And then there was another question about, where was it? Let's just do the full posterior and then let's see if I remember the other question. If there's one thing to take away from this book club, it's actually this diagram. I think this diagram, actually I know this diagram is the best visual for state space models in the whole thing. So it's really nice because you can see right here that the prior probability goes into this state, that the transition matrix is represented by A, and that the emission probability matrix is represented here by B, with Y being the output probabilities. Like, I think this is the nicest, clean one picture to explain state space models, and I'm gonna forever sear this in my head, and I'll put it in my docs as well. But it was hidden here. I shouldn't say hidden, but it was in this in the learning the parameters learning the parameters notebook. I'm not going to go through this notebook in detail because we'll be here forever, but now since we're in parameter estimation, we have to place some priors over the parameters. We place a Dirichlet prior over the 3 discrete states. Dirichlet distributions are super cool. If anybody wants me to talk more about them, let me know. But this is one of the super fascinating distribution. The important bits here is Kevin and Atal, or whoever wrote this notebook, I shouldn't say Kevin. They did a really good job explaining the practical portions of parameter estimation. So here we have full batch stochastic gradient descent and gradient descent, and a very nice graph showing that stochastic gradient descent is faster because you do multiple updates in one epoch. Super nice. They also do a great job explaining how stochastic gradient descent works. It's also great because this library is based on JAX that you can do stochastic gradient descent very easily in the code, and it's very easy to implement. It's a nice thing about stochastic gradient descent. I don't want to say it's a dumb algorithm, but it's like just a pretty easy, intuitive algorithm. You just calculate where you are at a particular point, and then you just look at the gradient, and you just go up, and then you theoretically eventually end up at the max, assuming that the whole distribution is convex. We'll talk about that in a second as well. They use another nice thing about Dynamax is you can plug in your optimizer. So in this case, they use Opdax, which is a optimization library also based on JAX. So it fully composes into Dynamax, and they set some parameters, and you get your answers. And in this notebook, they do a very good job explaining how close you get and why it's a little bit off, and then they go to expectation maximization, which is the more mathy way of calculating the prior probabilities. Sorry, not the prior probabilities, the posterior probabilities of the parameters. And they do a very nice comparison showing that expectation maximization converges much more quickly if you need to, and it gets way closer to the true data generating parameters. And where's I going with this one as well? That a very nice conclusion at the bottom. So I want to call it these caveats that SGD and EM are both prone to getting stuck in local optima. And then that if you want to determine the amount of states, you have to do a whole nother thing. So really, really good overview. Now, to answer Theo's question, which I've been putting off for quite a long time, is that okay? Don't quote me on this, but I'm pretty sure I remember hearing it, and from Kevin himself, and I'm going to give you the same answer here. Is currently we just do maximization because it's computationally fast and feasible. Dynamax does support MCMC in particular blackjacks, which we'll see later. Where is it? Here we go. We're going to get to this notebook later where you get full posteriors because you use Hamiltonian Monte Carlo sampling algorithm to estimate parameters rather than optimization algorithms. Whether you can use blackjacks here, I have not tried that. Actually, that would be a good extension as well to see whether you can use HMC to get a full posterior. But in this notebook, they just provide maximum likelihoods for everything, no full posteriors, Theo. But really good homework assignment to see whether we can plug in an HMC solver to get a full posterior here. And then for the casino HMM, when you're doing the Viterbi algorithm, I know that there is a permutation, again, not shown here, where you can get the top rank solution and then you can eliminate it from the solution pool to then get the next best and the next best and the next best. So then you end up with the ranked 1 through 10 best 1 through 10 most likely state estimates. But I think the computational complexity is too challenging to get the full posterior for this as well, because the amount of possibilities just forks and diverges too much to assign a probability to each particular one, especially for super long sequences. Again, don't quote me on that, but I'm pretty sure I either read that or remember that from somewhere. And I think that then goes to Charlie's point, and something else that I want to mention is that there's so many different pieces to state space models, right? That there's the representation of it with the states and the transitions and the emission probabilities, whether those are discrete or those are continuous, or whether those are time varying or not, whether those have covariates or not. And then there's so many different mathematical tricks that you can do to make things easier or harder. And then there's so many different computational algorithms that there are so many combination of these things that come together that make things either possible or not possible or infeasible and feasible. And a lot of this book club, frankly, is going to be me learning, and hopefully us learning together, what are the ones that are interesting to I what are the current implementations that are easy for practitioners to use. I I want you to keep that whole practitioner thing in mind, because that's going to be the very last thing that I talk about in this book, in this particular session. So let's go to this. This is the last sort of state transition that it will make, is redefining this this book club focus. So as you can tell, there's a lot of different angles on this. There is the whole, we could talk about the theory of it and how we ended up with state space models and the distributions, and we could take a very mathy approach, right? Like we were in a graduate program and we want to talk about how exponential distributions can be summed, and we can take integrals, and we could go that route. There's a route we could take where we dive into Dynamax and we talk about the code and how it's implemented and various computational tricks that are being used to make prior estimations smoother or faster, whatever. So there's a whole code angle to it, and then there's of course the applied angle, which is the notebooks, and then what is possible from the notebooks. In this whole book club, as you can tell in this session, I had jumped between a couple different states. I'd started out thinking like maybe I should explain the theory and the math, very simple, very similar to how we did it with the causal inference book club. And then once I went to the code, I was like, oh, maybe I should talk more about the code. It's so fascinating and interesting, and JAX is so cool. We should talk about JAX. And then I was like, well, that doesn't even solve the problem. Like, there are so many interesting things to do with state space models. Like, there's so many fascinating problems in the real world that it'd be solved. So I don't want these things to become 4-hour sessions. This session is already running quite long, at about almost going to be an hour and a half at the end. And I was thinking about what would be maybe the most interesting thing that I could provide to you folks. And my thought process was, well, Kevin already does a really good job explaining the math in his book. So I'm not going to do a better job explaining this than he has done. And I don't think me just doing a book reading would be all that interesting. And then looking at the code is already implemented. They've done a great job. I don't have it up anymore. Let's see. But they've already done a great job in the Dynamax library putting it all together. So me doing a code reading, again, you folks could just do that on your own. It feels like the unique thing that I can provide is, as a number of you know, I have come from an applied background. I was a person that didn't study this stuff in a degree, but came to it from being at work and needing to use these models, or now in retrospect, could have used these models at work to made conclusions faster, solidify my position, and provide a unique value to the company that I was working at, whether it was SpaceX, Sweetgreen, or now Google, or whatever company I work at. And I think that's the tact I'm going to take in these book club. I want to talk about why does this model exist, like what's useful about it, whether it be the categorical HMM model, later on the common filter model, which also has a really fun space-themed application, getting the Apollo missions to the moon, or SpaceX rockets into space. And then how it works from the driver's seat. So focusing more on the API and putting these models together, and how I'm test driving the car rather than the theory of the car and assembling the car, if that makes sense. So we're not going to talk about the theory of Carnot engines and heat cycles, which is what you do in a thermodynamics class. We won't talk about assembling a car, which is if you're working in a car factory, but we'll more talk about I'm a person that wants to drive this car. I don't really care about the engine or things like that to a great degree. I just want to get a feel for it, take it on some, laps around the test track. If I find some real world data sets, also take it on the road per se, and do that. So that's my prior of what would be interesting to you folks. I have a couple of clues from the chat that some people want to see jack stuff, some people want to stay on state space models. So my ask is, let me know. Go to Discourse and let me know whether you think that is the more interesting thing, and that's what you want to get out of this book club. You folks had said a number of things that were along these lines. Fluency in expressing diverse state space models. Use this as a forcing function to work our way up to more complex models. And how do I convert state space models into compelling cases for actions and decisions? That also led me on this path. So that's where my head's at. Would, as always, love to hear from you folks, so we can make this a useful club experience for everybody to learn together and maximize our joint learning as an entire group of folks rather than just me talking about what I want to talk about. With that, load up your questions in chat. I'm going to get to them. It'll take 20 seconds for this to get to you. But what I will talk about is the agenda for the upcoming book club. So, speaking about practical concerns, there's something coming up in my life. I'm going to be in New Zealand March 10th to March 31st. That's a big chunk of March and many Sundays. So what I think we should do, and I will post this all in Discourse so you don't have to remember it. It's that we have a book club next week. So in 7 days, we do another book club where we finish off the last 2 notebooks in the HMM category. So we talk through Gaussian HMMs and autoaggressive HMMs. And again, we take a very applied focus and work through these examples. I will do the same thing that I did here, which is I'm going to load these notebooks up myself. I'm going to mess around with them, try a couple things out, and I'm going to share my learnings, and then also talk about where I would probably use these models in my actual life. Since it's only 2 notebooks, and since we've covered the bulk of the HMM theory, I say we jump into these quickly, knock them out, and then we transition into linear Gaussian state space models over the course of March. So LGSSMs are an entire fascinating class of models in themselves. They can be used for forecasting and all sorts of stuff. There's a couple sections in my own book about linear Gaussian state space models that I also want to share with you. So let's do this over March, and we will do it in a more async fashion where instead of having maybe a live update, I will chat more using async methods, and then once we come back in April, we'll have our next live session. That way we can close out HMMs quickly, and then we have a good chunk of time to learn about linear Gaussian state space models over 5 weeks. That's my thoughts again there. I will post that all in Discourse for you folks. I want to say I'm really, again, looking forward to your feedback about the direction of this book club, the focus that we take during the live sessions at least. Not to say that we can't do a bunch of deep dives in theory and anything like that. We have the Discourse for you folks to share and post and to talk about the details. But just in the live sessions, that's what I'll be doing, likely. And then schedule-wise, another session next week, and then we'll take a long session from a long break from the live sessions and focus on async updates and things like that while I'm in New Zealand. All right. My voice is giving out. It's been a lot of talking. A number of things have come in on the chat, so let me pull the chat window up. Okay. So Theo says, agree. Tell us which parts of the book to read between sessions and learn the maths, which I find, and which bits of Dynamax code have implementations, but don't go over them in these sessions. Okay, Theo, I think that's what I'm going to do, exactly as you mentioned. I'm going to share this beforehand, probably ideally a day beforehand. I will post a notebook, and then I'll share which references and things I've used in my in either both my repository and also in the Discourse, so you folks can catch up on them. But I won't flip back and forth between them in the live streams. It is a very jumpy experience. It's not very fun for you folks to read. So totally agree on that. Then in these sessions, we can see real world examples of problems. All right, we're on the same page there. Nelson and Chad agree. So thank you folks for confirming that. I'm glad to hear that that we're on the same page there. Does anyone have a data set that we can share where there's an interesting problem for Dynamax? Charlie, let me try and find a real world data set. There are a couple. I want to point out in this particular for these particular notebooks, there was not a real world data set, and there isn't for these two. There are some more interesting data sets in the later notebooks, but that's a good point. Let me try and find a interesting sequence switching model, a sequence switching data set somewhere, that we can use for this particular categorical hidden Markov model. Uh, one good one that I don't know if we have the data set but comes to mind is actually for people that have phones, I think all of you, the accelerometer data off of this, you can use it as a state space model to determine whether people are running or hiking or jogging. Your Fitbit does this, by the way. It tries to figure out what state of exercise you're in by the patterns and movement that you're in. Or other phones can try and figure out which user is carrying them by just how they're walking while their phone is in their pocket. That's an interesting application. I'll see if I can find a data set there, but you have my commitment. I will be looking for a data set that we can work through together, and I'll post it to Discourse. Chad says, enjoy New Zealand. I was in Christchurch for a while. Oh, Chad, I might ask you for some recommendations. It's my third time going to New Zealand, but it's such a beautiful country that I am always happy to explore it. Yuri says weather as a data set. Weather is a good one, I have to say. It was used as an example in this this notebook, not notebook. This webpage that you go through sunny to rainy. So it's been super rainy for me in Southern California right now. So this actually is a good one as well. Actually that is weather is a nice one. Let's see if we can find some weather data sets for like, the Sahara Desert versus somewhere in Europe versus somewhere in the US. Actually, for you folks, let's all try and find a data set. Honestly, this would be quite fun. If I think it'd be more fun if all of us, for those of us who have the time, find a data set. Try and use the API. It's a wonderful API, really, really well done to build it. Grab your data, plug it in. And then see what you get. So find some weather data sets for whatever region you're in. Post that on the Discourse. That would be a really nice thing to do over this week. And it shouldn't be too challenging given this amazing library that we have. All right. With that, I do not see any other questions. I've already kept you here over an hour and a half, which is never my intent. I know you folks are busy. It's a Sunday. I will always try and keep these under 1 hour. So thank you for everyone for sticking with me for an hour and a half today. I appreciate you dealing with my random straight transitions again, trying to figure out what to do in this book club. And I'm really excited to kick this off with a strong start and see you folks in a week. So anything else, you know where to find me. Have a wonderful weekend and a wonderful week, and I will see you the fastest I've ever seen you again